Good afternoon, morning to you, Khépani. I'm very happy to see all you are here and to welcome you to another seminar for Dr. Khépani Raya Montaño. First, I would like to thank Khépani for accepting my invitation to share his research work with us. Let me briefly introduce Khépani to you. Khépani is currently a postdoc researcher at Nankai University. He received his PhD in physics from University of Michoacan in 2017. After that, he was appointed as a postdoc researcher at the Center for Research and Advanced Studies of National Polytechnic Institute in Mexico City in 2018. He was also appointed as an invited researcher in the University of Huelva in Spain at the same year. And then in 2019, Khépani joined Nankai University as a postdoc researcher in the School of Physics. Today, Khépani is going to talk about Parton distribution functions from its light from wave function. And Khépani will be very happy to answer your questions during the talk. So I will now pass you over to Khépani. So Khépani, please.
So let me start quickly. So this is my collaborators in China, Professor Chang and Professor Roberts. In Spain, Professor Rodriguez Quintero, and the ECT star people, Daniele and Minghui. The idea is that we will use the light from wave function approach because from the light from wave function, we can compute many objects. We can get the PDA after a simple integration. We can use the overlap representation to get the generalized Parton distribution. And in some limit, we get the Parton distribution function. We can also perform some integration to get the evolution of the form factors. And because we are Dyson-Schwinger equation people, we would like to get our inputs from solutions from the quark DSE and the Meson-Bethe-Salpeter equation before projecting onto the light from. And these inputs come from this kind of equation. This is the Dyson-Schwinger equation and the Meson-Bethe-Salpeter equation. The quark, the fully dressed quark propagator, depends on itself, on the quark gluon vertex, and the gluon propagator. The Meson-Bethe-Salpeter equation depends on the fully dressed quark propagators, but also on a quark-anti-quark scattering kernel. So this is an infinite tower of coupled equations. We can solve them, but we will explore an alternative way, which is in fact more economic to compute these kind of distributions. So the alternative inputs will be to model the Bethe-Salpeter wave function from our knowledge of the Dyson-Schwinger equation predictions. So I will start with the Kaon as an example, because we have two kind of, we have the U and the S quark here. On the left hand, we have the Meson-Bethe-Salpeter wave function. On the right hand, we have three objects. This M object is the Dirac structure that characterizes the pseudoscalar meson. We are keeping only the leading term, namely the gamma 5. We have a product of quadratic forms in the denominators. Those come from the quark and anti-quark propagators and the Bethe-Salpeter amplitude. And these denominators are integrated with, and I will talk about this later. Having the quadratic forms in the denominator, we can employ Feynman parametrization to combine the denominators, and after a series of steps, one arrives at this expression. Again, we have the Dirac structure and a scalar function and an integration over one of the Feynman parameters. In the denominator of these scalar functions, we will have something like k plus a mass-like term, and this mass-like term will carry on the dependence on the final parameters and the model parameters as well. The Nakanishi weight that we have over here will play a role in determining the mesons observables. And we will use the realistic Dyson-Schwinger equation predictions to model this object. In particular, we will use Minghui and Daniele's result on the Pion PDFs benchmark. So for that, I will give you a quick reminder of this result and why we trusted it so much. So in the rainbow ladder truncation, which describes very well superscalar mesons, the collection of symmetry preserving diagrams is this, the A, B, and C diagrams. In 2014, Professor Chang realized that we need the BC diagrams in order to restore the symmetries, namely the momentum conservation. We compute some moments at the so-called hadronic scale, which is the scale in which the purely balanced picture is the correct picture. And from the moments, we reconstruct and obtain this black curve. We compare the Dyson-Schwinger equation result with a Parton-like model. And what we see is that we have a dilation. This dilation to the emergence of hadron mass and the dynamical chiral symmetry breaking. And the same happens in the PDA. And this dynamical chiral symmetry breaking will manifest in everything, wave functions, form factors, and so on. Now we evolve the Dyson-Schwinger equation prediction for the valence, and we can get the valence, the glue, and the C at the scale of 2 GeV. What we learn is that at the scale of 2 GeV, valence carry roughly 50% of the momentum fraction. We find this pattern from the glue and the C. And now, if we compare with the experimental data, which in this case corresponds to the reanalyzed data, we find very nice agreement with the valence distribution. We also show the gluon and the C. And this gray band corresponds to lattice cross-section results. So we believe that the Dyson-Schwinger equation results are robust, so we will use those as benchmark for the light from wave function. So coming back to the light from wave functions. The pseudoscalar light from wave function can be written like this. We have the Bethe-Salpeter wave function and the operator that projects it onto the light front. The definition of the moments of the distribution is this. And if we combine the definition with that equation over here, we have this thing, taking the trace and playing the same game of the combining denominators and the algebraic tricks to change the order of integration, we arrive at this expression. Now, because of the uniqueness of the Snelling moment, we can relate this term in brackets with the light from wave function and get this. This compactness of the result is a merit of the algebraic model, and you can check, for instance, this reference. The light from wave function should be very influenced by the form of the rho. In particular, we have this kind of dependence. Now, if to study this influence, think about the chiral limit and take this asymptotic model. We produce the asymptotic profile of the PDA and the Parton-like profile of the PDF. If we put a power nu over here, we will get the power nu here and the power nu here. So this has a strong influence on the distributions we compute. Our choice is merely given by experience and analysis, is this form. And we have fixed the parameters for the Pion sector to match Minghui's PDF, the parameters in the Kaon to produce the Dyson-Schwinger equation result for the Kaon PDA. We have some values here. The masses of the U and the S quark can be understood as constituent quark masses, and we get these values from the realistic Dyson-Schwinger equation solutions. Now, what we produce is the following. This is the light from wave function for the U-quark on the Pion, and the equivalent for the Kaon, and the PDAs they produce. We have a smooth fall at the endpoints. The PDAs are dilated with respect with the asymptotic profile, and we have sufficient broadening to be consistent with the Dyson-Schwinger equation predictions. And as you see, the Kaon PDA is a little bit skewed. This is a consequence of the mass difference of the S and the MU quark. Taking a closer look to the Pion PDA, we compare with the Schwinger prediction. We see that we are very close to each other. Although we have not employed the result for the PDA as to fit our model, we have employed the PDF. But since the PDF is closely related, we expect to have good solutions for both. This is the relation for the PDF, this is the relation for the PDF. Same exercise with the Kaon, and this is what we get and compare with the Dyson-Schwinger equation prediction. Now, GPDs from light from wave functions. In the overlap representation, we can write the valence-quark GPDs as follows. We have now three kinematical variables: the momentum fraction, the skewness, and the momentum transfer. With this approach, the positivity condition for the GPD is automatically fulfilled, but this is only valid in the DGLAP region. And an additional merit of this approach is that it has been proved to be compatible with the diagram approach. And this is the Pion GPD for the U-quark and the Kaon GPD for the U-quark. Now we will take the front slice, the slice that corresponds to 0, because that is precisely what the PDF is. Now we have the Pion in blue, the Kaon in red, and I'm comparing with the Parton-like profile I showed you before. Again, the PDFs are dilated as a consequence of the emergence of hadron masses. Again, we have the smooth fall at the endpoints, but with the proper power law, namely a 2 instead of a 1 as in the PDA. Just to compare the momentum fraction carried by the U-quark and the Pion, because we are working the isospin symmetric limit, this is exactly 50%, but for the Kaon we have 47%. This is valid at the hadron scale. In this scale, the fully dressed quasi-particles of the valence-quark are the correct degrees of freedom. Thereby, all the momentum is carried by the valence-quarks. And later, the specific value of this scale from the process-independent effective charge of QCD. In this slide, I compare on the left side panel our PDF as compared with the Daniels and Mingwei result from Dyson-Schwinger equations. This, by construction, should be in good agreement, and you can see the degree of accuracy if we compare the moments. Now for the Kaon, we have preliminary results on the Kaon distribution function from the Dyson-Schwinger equations. I'm comparing with these preliminary results. Here the agreement is not as well as this, but this is the degree of sophistication that we have with our model. Not too bad. And now only to sketch that the small deviations are not really so important, let's take a look at Mingwei result. If we evolve to compare experimental results, any difference becomes practically irrelevant because it will be contained within the uncertainty of the initial scale. With that in mind, now let's proceed to something else. The form factors. The electromagnetic form factor is basically the dependence of the momentum transfer, t variable of the zero moment. This is the definition, and because of the polynomiality properties of the G, can safely take the skewness variable to 0. So our DGLAP GPD is enough. And now, to get the form factor for the meson, we combine the form factor for the quark and the antiquark, and we put the proper weights, which are essentially the electric charges. For the Pion case, it is very simple if we deal with the spin symmetry, because we merely have this. And our prediction pretty well with the GLAP experimental data. And this is the charge radius we obtained. A little higher, but it's okay. I will say that because we are not tuning anything for this is acceptable. Now, also compute the t-dependence of the first moment, and that will be what it's called as the gravitational form factors. This gravitational form factor, θ2, which is related to the momentum distribution inside the meson, can be directly obtained in the limit of a skewness variable to 0, again, or where the GLAP GPD is enough. And moreover, to evolve this θ2, we will only require the evolution of the GLAP equations. In the isospin symmetric limit, this is basically 2 times the integration corresponding to the U quark, and this is what we get, the red curve. And I'm comparing with the electromagnetic form factor. As you can see, this gravitational form factor that defines a mass radius is harder than the electromagnetic form factor. And actually, if we take this ratio, it will be 4 over 5, I'm sorry. The θ1 gravitational form factor, this is harder for us because, first of all, this is a D term. And although an extension to the ERBL region is possible, this extension is not sufficient. We need to fix this D term somehow. We have some help, and specifically from the soft Pion theorem, which implies that we get this identity at t equals 0, and we can fix the θ1 at t equals 0, but not sketch the t-dependence. So in order to get the additional form factor in the light and wave function approach, we will need some external inputs. Now let's talk about the evolution and the evolution of the distributions. Our idea is to define an effective coupling such that these equations here are exact. The equations resemble the leading order, the GLAP equations, but we want these equations to be exact at all orders. At the same time, we want to identify at which scale the valence picture, again in which the fully dressed quasi-particles are the correct degrees of freedom, is the correct picture. Fits of the process-independent effective charge can give you the answer. And let me talk about a little bit about the process-independent effective charge. What I mean with the features, I mean the saturation in the infrared, the connection with the perturbation theory in the ultraviolet, and the smooth transition between the two domains. And a natural consequence will be the absence of the Landau pole. So with that idea, we define a coupling that we call the all orders hypothesis. This expression captures what we want. We capture the saturation in the infrared. We capture the connection with the one loop coupling in the ultraviolet. And if we take this profile function n, which ensures reserved, and evaluate where the pole is supposed to be for the one loop, we get a mass of 0.33 GeV, and this is a screening mass that will determine transition between the domains, infrared and ultraviolet. And thus, we identify this screening mass as a hadron scale. And since we are conservative people, we introduce a 10% uncertainty on the hadron scale. Now, starting with the valence distribution we have computed already, we can generate the gluon and C distributions using the evolution equations. Starting with this result for the Pion, over the GLAP equations, we can get the valence at the scale of 5.2 GeV, the experimental scale, the C, and the gluon GPDs. And now we play the same game. We take the forward limit to the PDFs. We have the valence PDFs in agreement with the reanalyzed data. We have the glue, and we have the C. Here, the gray band corresponds to the lattice cross-section result. We'll find within the errors, we find an agreement with them. And an important thing of this is that the lattice cross-section result, as explicitly mentioned in the manuscript, favors a large exponent of 2. Just as we do, and just as QCD does. But also, if we take a very different approach, the light from Hamiltonian QCD approach, after proper selection of the counting rules, by rule number 2 by Professor Chang in this reference, we can also find valence-quark PDF that favors the exponent of 2, and it's in agreement with the reanalyzed data. So we have different treatments which are vastly different that arrive at essentially the same conclusion. Now we can sketch the gravitational form factors. This is the valence gravitational form factor at the scale of 2. Our result in blue, and in red I'm comparing with an earlier result from this PhD thesis. We find the lattice result harder than us. We would like to have nothing to compare with. Perhaps there is. But the important thing here is we can also generate the gluon and the C distributions, starting with purely valence distribution. And because the valence and C at a different scale are generated from the valence at the hadron scale, naturally we have this syndrome. Valence plus the C plus the gluon of the θ2 is equal to the valence this hadronic scale. For the θ1, we cannot do much. We just fix the value at t equals 0 with the help of the Pion soft theorem. Now, because we have splitting functions, the GLAP equations, after a series of algebraic steps, and following also our all orders hypothesis for the evolution, we can get a 3D of the gravitational form factors. We can plot the T, the momentum transfer dependence, and the scale dependence. In the previous slide, I show you the slice that corresponds to T equal 2. And we can also take a look at the slice that corresponds to T equals 0, because that is very interesting. This corresponds to the momentum fraction evolution. Our results are the solid lines. And I'm comparing with some results produced by the X-Filter collaboration earlier this year. Here is the valence and the glue, and here is the valence and the C. Now, for the Kaon, the challenge is bigger. However, we now have available a preliminary Dyson-Schwinger equation result, which I am showing you in this plot on the left. This is the UK divided by the U-pi ratio that compares fairly well with the data, although it is clear that we need more data. This result is also compared with the lattice QCD calculation. And what we produce in the light from wave function approach is this plot on the right. The blue one corresponds to the valence ratio, UK divided by U pi, and the form is very similar to the preliminary Dyson-Schwinger equation result. And again, we find some kind of agreement with the data. We can also produce this ratio for the C and the gluon. This is the C in red, this is the gluon in green, and some momentum fractions to compare with, the scale of 2 eV and the scale of 5.2 eV. And so in comparison with the Pion, precisely at this experimental scale, the Kaon will carry a little more momentum fraction for the valence that as it does for the Pion. A very important issue of this Pion Kaon is that we are employing the same scale, the same initial scale for both mesons, and this scale is not being tuned to produce this ratio. This scale has been defined from the effective coupling I showed you before. And although I produce quite large errors for the independent distribution functions, when I take the ratio, these errors basically cancel. That's why the error band is too narrow. So now we are in position to give some sort of summary. Using the Dyson-Schwinger equation prediction, Pion PDFs as benchmark, we have modeled the Bethe-Salpeter wave function. We have observed consistent features for the Pion distribution amplitude, such as the dilation at the model scale, a good agreement with the Dyson-Schwinger equation prediction for the PDA and the lattice as well. We obtained the GPD employing the overlap representation. This representation also ensures that the positivity constraint field is limited to the GLAP region, but is compatible with the diagram approach. It is possible, and we will do it at some point, to extend our calculation to the ERBL region. By construction, we are imposing the connection with the Dyson-Schwinger equations prediction. We have some implications. The keen agreement with the reanalyzed data for the valence PDF, the large X behavior by QCD, namely the 2 exponent, and we have been seeing compatibility with the lattice cross-section results. For the electromagnetic form factor, well, we find some consistency, and combining these properties of the PDF, PDA, and the electromagnetic form factor, we believe that we can trust the off-forward quantities. And in that case, we have also computed the valence and the CGPDs. However, to get the other gravitational form factor, the θ1, we still need the term. And we will require external information that we cannot get from the light from wave function approach. An important point here is that we have made an important connection with the running coupling. The process-independent charge of QCD gives the idea to define the effective coupling for evolution. And at the same time, it provides a definition for the hadron scale. So this is a scale that it is not tuned to produce any set of results. This is very important. So, given all of the properties and results I talked about in connection with the Pion, we believe that both the Pion GPD and the light wave function also come from the model calculation, are in fact promising candidates to be really close to the real objects. For the Kaon, on the other hand, we have been able to capture some qualitative features, as the dilation of the PDA, the dilation of the PDF as well. I didn't show it here. In the future, well, actually, we now have this available. The Dyson-Schwinger equations prediction will help us to further constrain the K electron wave function. We have found that the ratio of the U in the Kaon and the U in the Pion produces a nice agreement with experiment, and through evolution procedure we have been able to also show the C and the gluon ratio. And once we get the same degree of sophistication that we have achieved with the Pion, then we will be very proud and confident in Kaon electron wave function too. Something important here is that the gluon and CK and GPDs are within reach. It is just a matter of time. And with that, we will get a very comprehensive picture of the distribution of Kaon. So in general, this meson demands a little bit more work. So now, because I have a little extra time, I would like to something that we realized with when we were dealing with the all orders hypothesis. I am borrowing these slides from Professor Rodriguez's talk last. This is the master equation that evolves the momentum fractions with the scale. We can have this equation for the GPD, but for the time being, we will limit ourselves to the forward limit, so we are dealing with the PDF. Here we have the anomalous dimensions that corresponds to the non-singlet and the singlet and gluon sector. Solve the equation, we can find a basis such that we get a diagonalization of these elements, like this. Now we have introduced this lambda plus and lambda minus, which are essentially anomalous dimensions for linear combinations of the singlet and the gluon sectors. Now, if we use the hadron scale, and the scale at which all the momentum is carried out by the valence quarks, we can find a particular solution for this system of equations. And the solution is given by this vector. This vector means we have no gluon content. All the momentum fraction is carried by the U and the D quark, the Pion. And if we plug this in our equations, what we get is this expression for the momentum fraction of the valence. At some scale, namely set F, we can write this moment in terms of the moment of the hadron scale, at the hadron scale, at this ratio over here, which eventually will be translated into this ratio. So focusing on the first moment, we can actually write equations for the C and the gluon momentum fractions written in terms of the valence momentum fraction, which at the same time is written in terms of the valence momentum fraction at the hadron scale. And we can see that we preserve the correct sum rule here, and we can also see that we recover the asymptotic limits. If the scale tends to infinity, these terms cancel, and we get exactly 3 divided by C and 4 divided by 7 for the glue. And this is the extra thing I wanted to mention, so I will come back to the final slide. And thank you very much.
Very good presentation, unifying all the quantities, starting from light front wave function to Parton distribution, amplitudes, Parton distribution function, and form factor, GPDs, etc. So it's the time for questions. Does anyone have questions or comments for Khépani?
I have a question. you may have mentioned this, but could you define again for me what the gravitational form factor is?
Yes. Basically, we are taking the first moment that defines the first moment is the defined linear combination of two objects that depends on the momentum transfer, theta 2 and the theta 1.
So,
The
but
theta
why?
2 gravitational form factor.
Yeah.
Yes?
So why do you call this gravitational form factor? Does this have to do anything with the energy momentum tensor?
Because
Or?
exactly, it has to do with the energy momentum tensor. In particular, the theta 2 will tell us about the momentum distribution, about the mass distribution within the hadron, and the theta 1, which is the one we cannot get from the light from wave function approach, has to do with the mechanical property, the shear and the pressure, called the gravitational form factor.
So that is exactly what would go into Einstein's equations, if you wanted to do that.
It should. Yes. This should feed back on the energy momentum tensor.
Daniele here, are there experimental data for these form factors, or do they plan to measure them? Can you measure them at all? Do you know that?
As far as I understand, you can. You can use, for example, dispersion analysis for the gamma to pi naught. And from this process, you can also get the generalized distribution amplitude, which is of course connected with the GPD, and you can actually get access to this kind of things. I also believe that the same process that allows you to extract the GPDs, such as the virtual content scattering, could in principle give you access to the gravitational form factors. I think this is something of the GLAP physics, but I'm not really sure. But from the lattice point of view, it is also interesting because we have now very good, but let's say very novel results for the PDFs. But for the gravitational factors, lattice people, the lattice results I have found still use larger Pion masses, so the comparisons are not actually very.
More questions?
I have another question, Khépani. For GPDs, there are a lot of constraints, right? I mean, there is this, positivity, but then you have a polynomiality in C and all this stuff, right?
Yes.
So, is it possible to well, let's put it in this way. How many constraints?
Daniel is writing message in the chat, so I can read it for you, Khépani. He is asking you how many constraints can you satisfy by modeling a GPD?
Okay, it automatically I satisfy the positivity constraint, and if I restrict myself to the GLAP region, I can get the polynomiality, but I cannot get the polynomiality if I take non-zero values of the skew analysis. And so this is important. At some point, we will need to perform the ERVL extension so that we can fulfill the polynomiality requirement. They only get the zero we can only satisfy it with the zero skewness.
More questions? Can I ask a question? Maybe I'm not very familiar with GPD, but can lattice calculate Pion GPD? Is there some lattice result for Pion GPD?
I have seen one result for the Pion GPD. I believe it's the LAP collaboration, something like this. And they actually computed it at a scale of 2 GeV. But typically, I mean, they actually got the GPD there, but typically you just found the moments. And this lattice result, I don't remember the people, but it came last year. So we have some lattice result for the Pion GPD. And we also have lattice results for the gluon gravitational form factor and for the valence gravitational form factors, which of course should be connected with the GPD.
Okay.
But still only the moments, right?
Yes.
Yes, no, I was wondering, I mean, I would say that you can, quote unquote, easily calculate the moments. But if you want to calculate the full thing, the full object, that's way more challenging. And people have just started doing this for the PDF, and it will take another decade before they start thinking about the GPDs.
They are just starting to calculate this GPD profile recently. We hope.
Yes, exactly.
Okay, we hope they can do better. So, are there more questions? If there are no more questions, let's thank Khépani again.